Hello students. So up until last class we looked into the triple integral. We also tried to work out few examples related to triple integral and how one can basically how to say evaluate these triple integral on a bounded region in three-dimensional geometry. So now that we have covered our double and triple integral, we will go to the application part of integral calculus, where we calculate the area of plane regions, we do some rectification, we calculate surface integral, volume integral, things like that. So today we will start with area of plane regions. So this is basically our new topic today. So we will start with our new topic, and excuse me. So this is basically our the topic, our how to say today's topic, which we start with. So let's go to the introduction part. So what do we mean by area bounded between a curve, bounded between 2 points and a curve? So we know that in our usual integral calculus sense, when we say that the area bounded between 2 points, let's say x equals to, so this is our y-axis, this is our x. So let's say x equals to a and x equals to b, and if this is a curve, then let's say f(x), then the area bounded between these 2 points and the curve is basically this area here, and it can be given by this integral a to b f(x) dx. So that's our usual definite integral formula for the area bounded between 2 points and the curve. And similarly, if we have a curve of, let's say, this type, so this one was the curve of y equals to f(x). Now suppose if you have a curve of this type, x equals to fy, and if you want to calculate the area bounded between the points, let's say y equals to c to y equals to d, then in that case your area bounded between these 2 points and the curve can be given by integral from c to d fy dy. So regardless whether you are integrating with respect to x or integrating with respect to y, it just depends on the context, what kind of curve you are given and what type of points you are given. All right. So this is just a how to say a definition where we calculate the area between 2 points and a curve. Now suppose you are given curves like, so we might be given curves like ellipse. Let's say x square plus by a square plus y square by b square equals to 1, or we can be given a hyperbola. So this is basically a hyperbola, x square by a square minus y square by b square equals to 1, and similarly several other curves. So what kind of area is bounded by this curve here and between 2 points, let's say x equals to given 2 points actually, or for this hyperbola. So we can be given any curve and some points where we from using that we can be able to calculate the area bounded between the points and the given curve. So that's what we basically mean by areas of plane regions actually. So we will do several examples where we calculate the how to say the area bounded between these curves and the points, and we'll see how much is that area basically. So for example, area bounded between an ellipse. So inside the ellipse, the area of bounded by this ellipse is actually pi ab. So we'll see that how we can calculate that. Now we can also calculate area between two closed curves, or simply curves. They don't need to be closed. So let's say two curves. So between two curves, so let the two curves, I have to write the definition. So, let two curves y equals to phi x and phi 1 x and y equals to phi 2 x intersect at 2 points, say intersect at 2 points, say A to C, AC and BD. So, they are intersecting at 2 points and let between these points the first curve lies above the second curve, So, that means we have x axis, we have y axis. So, that is my x equals to A, this is my x equals to B, and suppose we have a curve like this and then we have a curve like this. So, this point here is basically B comma D and this point here is basically A comma C, and this is the, so this is basically y equals to phi 1 x and this is y equals to phi 2 x, and that is the area bounded between these two curves. All right. So, if this is the area bounded between these two curves, then it can be given by, so such as this, such as given in the figure, then the area between the curves is equals to area under the first curve, So, we first calculate the area under the first curve and then we subtract the area under the second curve, and that will give us the area between them. So, this is area under the second curve, right. So, how do we calculate the area under the first curve? So, it is between these 2 points and then phi 1 x, and the area under the second curve is again between these 2 points and then phi 2 x dx. All right, and then we just calculate the value of the individual subintegrals and subtract them, and that will give us the area bounded between these two curves. So, that is another way to calculate the areas between these two curves. So, now let us consider an example and see how we actually calculate it. So, example 1, let us say find the area bounded by the ellipse x square by a square plus y square by b square equals to 1. So, we know that if we substitute a equals to b, then an ellipse reduces to a circle, and for a circle the area is pi a square. However, what can be the area for an ellipse? As I told you that the answer is pi a b, but how do we actually calculate it? We will see just now. So, first of all, let us draw an ellipse. So, this is our x axis, this is our y axis, and if we draw the ellipse, as I told you, I am really not good at drawing. So, this is our ellipse, that is basically the semi major axis, this is semi minor axis. So, this length is a, this length is b. Now, we know that an ellipse is symmetric along both the axes. So, if we can be able to calculate the area in any one of these quadrants, then we just multiply it by 4. So, whatever the area is here, it will be the similar area here, it will be similar area here, and then it will be similar area here. So we don't have to calculate over the entire ellipse, we just calculate in for one of these portions of the ellipse, and then we just multiply it by 4. All right. So let's see how we can do that. We can write it that the ellipse is symmetrical about both the axes, about both the axes, about both the axes or coordinate axes, so that the two axes divide it into 4 portions, whose areas are equal, So now we will basically integrate this region. So we will basically integrate the area bounded between this curve and these 2 points. So x equals to 0 to x equals to 1. So the area, let us say this is O, A and B. So the area of the region, so area of the region O, A, B, O is equals to integral from 0 to A y dx, and our y is basically b times 1 square root of 1 minus x square a square dx, right. So this will be b by a integral from 0 to a square root of a square minus x square dx. Now this we know that from our usual integral calculus formula that this will somehow the answer will involve sine inverse x. So we can write now the value of that integral. So it will be x times square root of a square minus x square divided by 2 plus a square by 2 sine inverse x by a integral from 0 to a. So now if I substitute the values, then this will reduce to, so when x is a, this is 0, when x is 0, then this is again 0. Now this one is a square by 2 sine inverse a by a minus sine inverse 0. So ultimately this is 0. Now this is sine inverse 1. Sine inverse 1 is pi by 2. So ultimately we will have b by a times a square by 2 times pi by 2. So this will be pi a b by 4. So from here the area of OABO is basically pi AB by 4. Now since we just talked about that ellipse is symmetric along both the axes, so it is symmetric along both the axes. So that means if we calculate the area of any one of these portions, then we just multiply it by 4 and then it will be the entire area of the ellipse. So to calculate the area of the ellipse, so this implies the area of the ellipse is equals to 4 times area of the portion OABO. So that means 4 times pi AB by 4. So that means pi AB. All right. So that's basically the required area of an ellipse or area bounded by the ellipse. So this is one such example where we can calculate the area of a function or of a given curve bounded between 2 points, and then we multiply it by 4, and that will give us the area of the entire portion or bounded by that curve. So that's how we calculate the area of this plane region. Next we consider another example. So, prove that or we can basically say evaluate. So, we will just evaluate, that will make it more interesting. So, evaluate the area of the region bounded by the curve a to the power 4 y square x to the power 5 2a minus x, right. So, let us write the solution. So, that is my x axis, this is origin, and that is my y axis. Now, we have x to the power 5 2a minus x. So, that means and here we have y square. So, that means obviously the point 0 0 lies on this curve, because it's if we substitute x equals to 0 and y equals to 0. So, the point 0 0 lies on this curve. So, that is pretty much straightforward. So, one of the points on this curve is 0 0. Now, we have x equals to we have 2a minus x. So, when y is 0, then basically x is equals to 2a. So, the curve, so this is basically x equals to 2a. So, of course, it passes through the point 0 0, and then it also passed through the point 2a 0, because when y is 0, x is 2a. So, it passes through the point x equals to 2a and y equals to 0. And now, we have y square. So, for y negative and y positive, it will have the same value. So, that means it also how to say it also lies I mean, in a way, both sides of x axis in a way. So, that means it forms basically a loop. So, what I am trying to say is that it forms some kind of looping. So, it will look something like this, not exactly of this figure, but it will look something. So, a little bit down here and then up here, and then a little bit down here and then up here. So, that is how it will look like, and this is the region bounded by this. Let us call this as E. So, this is the region that will be bounded by this curve. So, the curve, we can write now, the curve consists of a loop lying between the line x equals to 0 and x equals to 2a, and it is symmetrical along the x axis, because the values of y are minus of square root of minus plus a square root of x to the power 5 times 2a minus x. So, that means y is lying both above the x axis and below the x axis. So, and that's how basically it will form how to say a loop. So, it has some part lying above the x axis and lying below the x axis. So, this is what we mean here. So, basically the required area. So, the required area is equals to 2 times area of the region. Let us give it a name, OA, say some point at here is B. So, of the region OABO in a way, and the area of the region this much only. So, area of the, so we just calculate the area of this region and then we just multiply it by 2. So, the area of this region only will be integral from 0 to 2a and 0 to 2a, and for this this will be 2 by, so this will be 1 by a square x to the power 5 by 2 times square root of 2a minus x dx. All right. So, that means we have 2 by a square integral from 0 to 2a x to the power 5 by 2 square root of 2a minus x dx. All right. And to evaluate the integral, now to evaluate this integral, we have a square root form. So, we substitute x equals to 2a sin square theta. So, we just substitute x equals to 2a sin square theta. So, that we will end up getting some kind of cos square theta that will neutralize the square root. So, that is what we will do here, and ultimately if we do that, then the whole thing will reduce to, so the whole thing will reduce to there is no such symbol. So, the whole thing will reduce to 2a square integral from 0 to pi by 2 2a to the power 5 by 2, then we will have sine to the power 5 theta, then we have a square root of 2a of course, then we will have cos theta, then we will have 4a sin theta cos theta d theta. So, ultimately this whole thing will reduce to 64a square, 64a square integral from 0 to pi by 2 sin to the power 6 theta times cos square theta, right. So, sin to the power 6 theta times cos square theta. Now, this falls into our reduction formula category. So, we have already evaluated integrals of this type in our reduction formula type situation. So, this will be 64 times a square, and then we will have 5 times 3 times 1 time 1, and then this will be 5 by 8. So, basically what I am trying to say is that 5 by 8 times 3 by 6 times 1 by 4 times 1 by 2. So, multiplication times pi by 2. So, if we calculate the whole thing, then it will be pi by 4 pi a square, and that is basically our required area of this, where is that, of this region. So, of this entire region. So, we did not have to calculate the area of the whole region, since it is symmetric about the x axis. We just calculated the area of the above region, and then multiplying it by 2 will give us the area of the whole region, and that is what we have done, and the required answer is 5 by 4 pi a square. So, this is how you calculate the area of this plane region. Next, we have a curve that is given something like this. Let us consider another example. So, sometimes instead of having a polar instead of having a Cartesian coordinate expression, you may have a polar coordinate expression, and the curves like cycloid or lemniscate of Bernoulli, things like that, they are expressed in a they can be expressed in terms of a polar coordinate system as well. So, let's look at one such curve. So, find the area enclosed between one arc of the cycloid x equals to a times theta minus sin theta, and y equals to a 1 minus cos theta, and its base. So, basically if you look into any 2D coordinate geometry book, then in that case there you can be able to see all these nice figures, and the figure for cycloid can be given by something like this here, let us say A and P. So, just one arc and its base. So, this is the base and that is the one arc. All right. Next, so this is y0 AP. All right. So, to describe the first arc, of the cycloid. So, to describe the first arc, of the cycloid, theta varies from 0 to 2 pi, and the coordinates of O and A are and the coordinates of O and A are 0 0 and 2 a pi 0. So, here this point is 2 a pi 0 and this one is 0 0. So, this is basically the 2 points where we how to say evaluate the area of this cycloid. So, let us do that. So, the required area is basically integral from 0 to 2 a pi y dx. So, we can write it as 2 a pi. So, we have basically y equals to integral. So, this is basically 2 a pi. So, we have y equals to a times 1 minus cos theta, right, and then we have dx. But since this is in theta and that is in dx, so we have to somehow transform this x into a theta form. So, we know that x is basically a times theta minus sin theta, all right. So, theta minus sin theta. So, from here we have dx equals to a times 1 minus cos theta, is that correct? And when x is 0, then in that case theta is 0, and when x is a, then theta is 2 pi. So, we can write this here which is basically the required area. So, the required area is basically integral from 0 to 2 pi a times a. So, this is a square and then we have 1 minus cos theta whole square d theta, all right. So, now we can break this whole thing into integral from 0 to 2 pi 1 minus 2 cos theta plus cos square theta, then we adjust the plus cos square theta, then we adjust a 2 here by adjusting a half, and this will reduce to integral from 0 to 2 pi 1 minus 2 cos theta, and if we adjust that half, then there will be a 2 here 1 plus cos 2 theta d theta, and now we can integrate this individual term one by one. So, this is fairly simple and I am pretty sure you can be able to do that. So, this will this whole thing will reduce to a square times 3 pi basically, and 3 pi a square is the required answer. So, in this case we were given a cycloid. So, from here first of all we need to find out how does that curve look like. So, sometimes you also need to practice with curves, so that just looking at the curve you can make out, okay, this is the way this curve should look like. And to describe the first arc of the cycloid, we can see that theta will vary from 0 to 2 pi, and the coordinates for O and the point A are basically 0 0 and 2 a pi 0, and the required area would be then this one here. So, this is our required region or the area which we want to calculate. So, of course, x will vary from 0 to 2 a pi and y dx. So, this is the y part. So, y dx, and we substitute the value of y here, and dx can be calculated from here, which we have done in at this and the second page. So, here I have forgotten a d theta. So, d theta, and then we just substitute the value of dx here. So, this a square will come here, and we'll have 1 minus cos square theta. So, it's just a simple trigonometrical calculation, and I'm pretty sure you can be able to do that, and ultimately we will obtain 3 pi a square, which is the required area of the cycloid. And its base, between the cycloid and its base. So, we'll stop here for today, but in our next class we'll start with a new example related to area of plane regions, and we'll how to say practice maybe at least 1 or 2 more examples to clarify that concept, and then we'll move to rectification if time permits. So, thank you for your attention, and look forward to your next class.